There it goes.
Good morning. My name is McKinnon. I teach at South Junior High in Boise, Idaho. I teach 9th grade physical science, physics and chemistry, and introduction course. I also teach online earth science. I also teach driver's ed. And that's a little bit about me.
And my name is Whitney Eggers, and I am teaching at Emmett Junior High from Emmett, Idaho. And I have been teaching biology for the past, this will be my 20th year. 7th grade life science, but this year I will be teaching physical science for the first time in about 15 years.
A bit about our mentors. We'd like to show them on the screen just so you can see them. And I can do that here, I think. Yeah. All right. This is Behzad, and he is an amazing person and a great engineer and a great mentor. He has had a specialty in modeling and simulation of the Mars exploration missions, and specifically entry, descent, and the landing simulations. He's the one who took all the input and created the simulations to give them the references they needed to have a successful mission.
And our other mentor was Eric Queen. And Eric has worked on simulations, modeling, aero maneuvering of entry, descent, and landing for different missions, including MER, and the Mars Phoenix, the Polar Lander, and the Mars Science Laboratory mission, and he's been a really big help.
All right. The topic of our lesson is, what does it take to land on Mars? We came up with this topic simply because our mentors did that. They came up with all the simulations to get to that point. What does it take to land on Mars? They did the simulations, they ran them, they checked them, the atmospheric stuff, all the things, all the different scientists who had contributions, gave the information to these guys, and they ran the simulations to make it work.
So as you can see on this next slide, our mentors, Behzad, helped us create the simulation for our lessons using MATLAB and continually supported us in developing and engineering our SFUBE launch system. I'd like to talk about Behzad for just a minute. He was the technical lead, and I'm pretty sure this was his first year in doing that. He organized a lot of speakers throughout the entire program, and I know he spent many, many hours doing this, and we really appreciate that. During our first week, we spent a lot of time engineering our SFUBE launcher, and we actually were invited to Behzad's house, and we spent about 3 hours putting it together, doing a lot of drilling, just changing things around. We had to use a saw in the pouring rain, and we spent quite a bit of time there, so that was above and beyond the call of duty. So Behzad also ran simulations for us on his MATLAB, and that really was helpful and actually complimented us on our system because we were actually fairly close within reason to the information we needed to get. Behzad lined up additional speakers for us, which was really helpful, and actually one of the speakers, Jeremy Schneider, we actually used one of his posters to help us quite a bit with our presentation. Above and beyond, I have taught biology for a long time, so Behzad took painstaking effort to explain to me what a Newton was with a lot of help from Aaron. These guys have been really supportive, and even though I have a biology background, I will be teaching physical science this year, and at least I have a lot of information to draw from and can really help show students real-life application for what they need to know about advanced application physics and what they could do with it. So thank you, Behzad.
Eric, we met him the first week. He had to leave us for a little while, but when we came back, we had a chance to access his intelligence and creativity. So we went to lunch, and we had a problem. We did not have a solution to our problem. Behzad did not have a solution to our problem. We had several solutions that could have worked. The opportunities to get them didn't seem real feasible, but then Eric came up with a wonderful solution. And so that was great. Besides making the simulations for us and running the math in Octave, Excel, and MATLAB, they did a great job of giving us ideas, working with us, and allowing us to be a part of the process that this whole 2 weeks has been. Engineering, simulation, modeling, which is what we did with these guys. Looking at ideas and doing it over again, running the problem, coming back and making changes. So the whole experience of designing this lesson plan was very beneficial to me personally, and to see what these NASA engineers do, and that they're real people, and that they have the same problems that we do, and looking at a situation and making it work.
We'll bring up the next image for you. Aaron and I have a similar educational philosophy. Our courses are introductory in nature. We both teach at a middle school level, and they are very hands-on. We want students to be able to experience science and have fun doing it. A lot of students are coming from elementary systems, 6th or 7th grade, at least for me, and so they're experiencing science for the first time separate from all their other coursework. So we do like to have them have a good time doing it. Having a biology background, we spend a lot of time doing dissections and things like that, but now I have new information, and I launched a rocket for the first time, and so my students will be launching rockets when I have to take on physics in the second half of the semester. So a lot of what we do for the introductory prepares the students for more rigorous classes in the future. Some of the math applications that we have, you may have to do a little bit more step-by-step approach to show students how to manipulate an equation, but nevertheless they can still, do things simply and not be fearful of the math in an equation or something. So we try to keep it open and fun and understandable for them so that they'll want to continue.
The lesson overview and content focus. Our lesson focuses on students' understanding and experience engineering and design process through modeling and simulation. Basically, that's it. We will have, of course, some prerequisite knowledge. The content focus will be on reinforcement of those, specifically Newton's laws, air resistance, friction, and the conservation of energy. And so we'll be looking at basically grades 8 and 9. They should have a basic knowledge of Newton's laws, kinetic and potential energy, and the conservation of energy, friction also. This would be perhaps an assessment, an opportunity to extend what we've learned, and then to, I think, really emphasize what we found out this week is missing in a lot of the STEM activities, the engineering part. So we will have a lot of engineering design, a lot of modeling to get to a certain point and building up to the simulation that our engineer mentors have prepared and we've worked with.
So our learning objectives are that students will be able to brainstorm and answer to unknown and new situations by using prior knowledge and simulations. Throughout our lesson, we have lots of opportunities for students to become engaged by an opening question or a joke or an activity or something that makes them want to think and want to do things. The students will be able to design their own, what we call a spube, after they've already taken some initial masses and done some simulations with a regular sphere and a cube. That's how we got our spube. And they'll be able to make calculations, as I mentioned a little bit earlier, by actually using the math. A lot of the kids at the 7th grade level come in not being very strong in math, so we've made some adaptations to actually doing the math where they have units and directions about where to place the certain numbers in the formula so they don't have to worry about where to put it, in the hopes that eventually they'll gain the understanding of more of the math as it comes along. And ultimately they'll be designing their spubes on their own and launching them, and Aaron will show us that a little bit later.
Doing a little discussion with pedagogy. This is the entire class that I teach, models constructivist thinking. I like to call it the zone of approximal development. When I think about it that way, and if I could just show you, we all have a certain knowledge at this point. What we give them in physical science takes everyday life and explains it, but they only know everyday life. So when we explain it, it makes them get a little bit bigger. So basically, every lesson I give is a discrepant event, because they don't know the answers yet, and we have a chance to explain it. It's a wonderful class to teach because it is introductory. The light bulb's going on all the time, and kids have a great time seeing these things happen in real life. We don't get into the math too much, or the simulations at this point are going to be pretty basic, but it's a great opportunity for kids to see, well, I don't know the answer, but I can figure it out. And that's what the simulations in this week has really helped us see. Okay. Knock, knock.
Who's there?
Curious neighbor number 1.
Curious neighbor number 1, who?
Mr. McKinnon, what are you going to do at space camp? It's so cool that you're going to NASA. Knock, knock.
Who's there?
Curious neighbor number 2.
Curious neighbor number 2, who?
Mr. McKinnon, what are you going to do at space camp? It's so cool that you got there, but what are you going to do? Knock, knock.
Who's there?
Curious neighbor number 3.
Curious neighbor number 3, who?
It's so cool, Mr. McKinnon, that you're going to space camp, that you're going to NASA. What are you going to do? I heard that question lots of times as we went out into the communities and we talked with our friends and neighbors and the different businesses to get support for this program. And I really didn't know what this week was going to be. My prediction, my hypothesis, was that we would have the chance to sit down with engineers, pick their brains, find out what they do, look at the stuff they do, and then apply it or incorporate it into our lesson plans. And we've done exactly that. I could not have asked for a better experience to say, now I know what rocket scientists and rocket engineers do. And it's been a wonderful opportunity to take that and think about what we can do with that in our own lesson plans. So when I go back, I will say to all the people who I will talk to, we did exactly what we wanted to, and it was a blast meeting these people and having these opportunities. Going to day 1, we're going to take you through our lesson plan. It could be a week, maybe a little bit longer. You could run these activities or days. We decided to do it as days for this presentation here. We start off creating engineering teams. There's going to be different jobs throughout the different activities, so 4 members per team, and then a basic brainstorming topic. If kids, and this is again our discrepant event, kids haven't thought about what engineering is. This will be the first introduction to it. They may have had some brief explanations before, but this is the opportunity for them to think a little bit outside that box, beyond their zone of proximal development, and give them a challenge. What challenges are there in landing on Mars? I teach driver's ed. I go through that all the time with what challenges are there parking in a parking lot? What are the challenges for you to get into your driveway? And we talk about speed, and we talk about there's a bump, and what if there's something in the way? And we have to think about this angle, what we have to wait for. Is there going to be a change in time of day for all the different things? That's a small variable. Those variables are incremental compared to what the huge thing the NASA project is doing. But that is everyday life to me. It's everyday life for what the kids are doing. And so we gave them the challenge. What challenges are there in landing on Mars? What does it take to land on Mars? So the students will be working on a sheet that parallels PowerPoint you'll see in a little bit, and hopefully come up with the same challenges that the engineers do and what they've created. And so we'll give them time to do that, and also do a jigsaw activity where they can discuss among other groups, come back and talk, because we saw that. Bezod knew all the engineers. So did Eric. When you mentioned a name, they knew what that person did and how they related to their area of expertise because they communicated, and that's a very valuable thing. So we wanted to model in our classroom what the real scientists and engineers are doing. Taking a problem, figuring out all the variables, and then going around discussing to see if we can incorporate all those variables and then solving problems to those challenges. Okay. The interactive PowerPoint activity we have is, I think, a really great thing. We spent a lot of time on it, and it'll guide the students through what engineers do, and it'll compare the engineers' identified challenges to what the students generated. And I think it'd be kind of neat to do this as an experiment. Hey kids, here's a problem, and this is what you think the answers are, or what situations you'll need to come up with. Let's compare it to what the real scientists have determined. Let's take a look at that. I think the students, looking at that from a different perspective, may come up with something that the engineers may not have thought about, and we have a chance to open up that discussion. Going back to that slide, each of the slides will have a solution to those challenges through questions the kids get a vote on. I like saying science by democracy. Again, those are discrepant events. You don't know the answer exactly, but you can make a pretty good guess. Let's take a look at the guess and then see how accurate you were. So that we'll be able to see a simulation created by the engineers we talked to illustrate their solutions. This PowerPoint is modeled after a poster created by NASA engineer Jeremy Schneider for a presentation to middle school youth in Virginia. He showed it to us, and he wanted our input on it. So it made us feel good that we could help out a NASA engineer. So he showed us the poster, and we gave him some input. We made some modifications to it, and that became the impetus for our PowerPoint activity. We also have built in their time to visit and evaluate different NASA sites, the simulations, the videos. There's so much out there. This is what's going to get the other teachers in the district in my building excited for whatever topic they teach. There are so many neat opportunities for the students to look at. It doesn't have to be just math and science. There's all sorts of neat things. They've incorporated art. And so we'll have the students go through a selected few websites, but then let them play in there and evaluate what they think be important to them and give them that freedom of choice. On the slide here is a model of what our PowerPoint will be. So you can see here that the scientists came up with 5 different challenges that they figured that they would encounter on their way into Mars. So what does it take to land on Mars? The scientists came up with the different challenges in order from what Jeremy told us. And again, he and Behzad did the same job of taking all the different scientists' information and creating a simulation. Entering the atmosphere, entry guidance, slowing down enough to land, preparing to land, and the landing itself. So the students will be able to hover over, as you can see. Each of these are clickable. So there's the first question. Oh no, you're coming in too fast. You could burn up the spacecraft. Which craft would you choose to survive the heat? There's the challenge. Given to the students, predicted by the engineers. Choice A is the modern version that'll be launched in November of 2011. And then we have the shuttle, which the students are familiar with, that has been retired. And then we have the classic X-Wing fighter. Click here, and then they can choose on this. Let's say they choose this one. Correct. And then it gives some information that we learned from the engineers I did not know about, that I was really appreciative of learning about. The shape here, we found out, absorbs basically 99% of the heat created. During the simulation we'll be able to see the actual dials change as the speed changes, and watch this, and so we can talk about that. It also gives us a chance to talk about why there is heat as we talk about kinetic theory. It'll be traveling somewhere between 13 and 30 times the speed of sound. We've heard some different numbers, and we're working on getting that solidified because the scientists have to run different simulations to get that. Again, each of these points down here are hoverable, so as you hover over it, you can go back to the different challenges, the same challenges, the next challenge, or you can go home, so we'll go back. The shuttle is too big and too heavy. It will not fit inside the launch vehicle, the rocket, to get it to Mars. And then, of course, the X-Wing fighter, very maneuverable and precise out in space, but when we have it entering an atmosphere, it does not have enough heat protection. The simulation here was created by Jeremy. And I'm going to fast forward it a little bit and move it up to about here where we start to see out in space. You can see up here the altimeter, the relative velocity. Right now it's 57,000 meters per second. Horizontal velocity is very similar. And you can see here the altimeter going crazy now as it's entering the atmosphere and changing in relative to position to the surface of Mars. You can see the blasters, or the rocket boosters going on, orienting the capsule for an accurate landing. That's another question on here. That's the first time that that's actually happened with a landing on Mars where it's been controlled. I think this is a valuable simulation that shows all the dials here and all the input that was necessary. 1, 2, 3, 4, 5, 6, 7, 8, 9 different things just to get the simulation going. We'll go ahead and fast forward again. The simulation runs all the way through to the parachute dropping, the module using radar, which is another question. All these things in the simulation are answered, are discussed in the problems or the challenges that the engineers designed, looked at, and the students had a chance to correlate. We'll go ahead and stop that, and we'll go back to the slide. All right. After that, we'll have a couple, within this embedded, of course, is evaluation, opportunities for reflection, which I think is very good, a chance to see how they learned and what they learned.
So the students have had a couple of days, and remember, they're already in groups. They've done some brainstorming. They've done some constructive ideas on the board. And then they've had an opportunity to look at the PowerPoint, and they've also had the opportunity to be guided to some of the other websites. On the third day, Aaron mentioned a little bit earlier, we have something called Science by Democracy. Science by Democracy is where students vote on whether a given description describes either scientists or engineers. They'd have a little bit of a review of the interactive PowerPoint, some highlights, and some favorite sites that they've had the opportunity to take a look at. So Science by Democracy is a little activity, and it kind of leaves it open to the teacher For example, this particular one focused on scientists or engineers. Students would have the prior information to know what is a scientist and what is an engineer, and you could make up a little list as long or as short as you wanted. Me coming from a biology background, I would maybe say to the students, okay, I have a monkey, and he's in the jungle, and he's eating a banana, and I'm going to observe him. Science by democracy, is that a scientist or is that an engineer? And the students would raise their hands and be able to vote, and so it would be quick, immediate feedback. It's a little bit of an assessment in that respect. If I wanted to go on from that, another example, I could have said, I want to observe rocks on Mars. Excuse me, science by democracy, and so I'd have the kids vote, and they'd be able to tell me whether it was a scientist or an engineer. If you wanted to add the space idea to it, say I needed to collect some rocks and examine them, then science by democracy, and they'd have to tell me what I need. Be a scientist or an engineer. Well, I'd have to have a way to collect those rocks, so I'd probably need an engineer to tell me how to build something so I could gather up those rocks, so then the scientist could do his part of the idea. So that's one way to start differentiating between the different parts of the STEM with the scientist, the engineer, the technology. After that, there's an activity called throw, catch, or draw. This begins to give the students an introduction to a projectile and trajectories and the variables that influence the flight. So with you could have groups, or the groups would be going out to do this. Throw, catch, or draw is an activity you could probably do in the gym, or you could go outside depending on the weather. And in your little team of 4, one person would be doing the throwing, one person would be doing the catching, and 2 people would be standing on the sides, and they'd be actually drawing the path that the ball through. You could use a football or a regular ball, and so that would give the students the idea of the path that's being traveled, and some of the ideas as far as throwing the ball and how far they can throw it, things that would be involved like the angle that they're throwing the ball, how much force they're using to throw the ball, and that would give them some idea to start playing around a little bit with the force used to throw the ball and the angle at which it's being thrown.
We had a fun time, and this to me is exciting because I love going outside my room and having a chance to see the kids diagram, see what they can do, get their observations, and it really gets down to the very beginning of our simulation. We can only control 2 things at that point, angle and the force of the throw. And once they recognize that by themselves, they're able to go the next step, look at the other variables. And so this is the baby steps they get to our simulation. Gets them outside, gives them a chance to model, see, and create a little diagram and evaluate their diagrams. Talk about, we can introduce terms, apogee, we got the height, we got all these different things, and get into our simulation eventually. So the next day, of course, is getting to our Spube launcher. Our Spube launcher, it has a couple different things. It's simply a PVC pipe, bungee cords, and then the computer simulation experimentation to get there. It was a blast for me to create this. And so I would like to show it to you now. I can come over here.
They have you standing on the left.
Right here?
Yeah, in the corner.
Right here?
In the corner.
I'm right here. All right.
In the corner over there.
Oh, I know. I just want to talk about this. All right, this is the Spube launcher. As you can see, it may be construed by some in the administrative role as a projectile launcher, also known as a gun. We're calling it a Spube launcher. It has a maximum velocity that we've determined of about 7 meters per second. As you see, it does not shoot the ball very fast. We'll model it. It does show shows a great trajectory, and it's very consistent within our gross parameters here. And it was a lot of fun for me personally to engineer and design with our mentors. We had a lot of problems to solve with it, and we'll discuss those in a little bit, but I wanted to show you right here. Take the sphere, and we put it in there, and then simply pull it back. And you can pull it back to different parts. Of course, this is the variables that they'll be able to control. And Whitney almost caught it. We'll also be able to launch the cube, and with different coefficients of drag, and of course they'll get to that. I think they can all figure out that they have the same mass, they'll have the same force applied to them. There's a little bit of frictional differences, about the same velocity coming out, but they don't land in the same spot. What's the difference? So there's another variable. We've got force, how hard you throw it, or in this case, how far you pull back the plunger. We got the angle, and now we can talk about the aerodynamics, and we can add in a few other variables and I think that they'll see them. We're predicting that in 9th grade, as we develop these things slowly, they'll be able to see all these different factors. I need to explain, I'm sorry, how we came up with the words few. The engineering part of this, it gives them the baseline for finding all the data. It's simulation and experimental. We've got a process to get to that point. We'll show you the flow chart. But then we give them the engineering part where we cut these into different parts. With these different parts, they can glue them back together, any design they want, and then they'll have their SPHUBE, which is a combination of the word sphere and the word cube. They'll be able to launch it then and experimentally get the data and then go back to the simulation to guess basically what the coefficient of drag is. It's working backward to get to the same point. So in the simulation, we were actually going to simulate, experiment, and then the last part of this SPHUBE, use a combination of both. And that was, we engineered this design here and the entire simulation with Eric and Behzad. Without them, we couldn't have done it. We needed their expertise. And we feel that we've gained a lot and have a lot more knowledge ourselves. Thank you. We'll come back to the slides. All right. This is the flow chart that we came up with to get to our simulation. And so we have to measure the spring constant. And you can see a diagram of it there. So we had to hang a mass off the end of this, and the mass, of course, pulled down the bungee. We could then measure the distance and mark it at certain points along there, and that would correlate with the weight being pulled down. And we plug it into the formula, and that gives us our spring constant. That is our elastic potential energy. That goes down to the K value here, and we don't know what V is. V is our initial velocity. And then we have to calculate the X, which is how far we pull back to hit the certain target. And we experiment. Okay, we're experimenting to get there. Then over here is the simulation part. Okay, if you run this first and run the simulation, plug in the stuff that you know and make a guess at it, then you should be able to compare these two together and see what the difference is. When Eric ran the simulation, he had an initial velocity of 8.5 to get it to go 9 meters. For us to go the same distance, we came up with 7.8. And so our 7.8 initial velocity is relatively close to 8.5. Eric and Behzad were both happy with that, as were we. Here is a brief look at the Excel spreadsheet that Eric designed for us. And on the left here in the green boxes are the variables, and the students can change. And then the math on the right-hand side, the final range, will give us how far it should go. And again, we will have both ways, experimentally and simulation, to see how well they correlate, and then use that data to come up with this SPHUBE and come up with that. The challenge then. Using this data, the students should be able to figure out what angle and at what velocity, how far back to pull the plunger would determine the velocity, and that's in the simulation also, the K value, how they would need to launch this SPHUBE to go a certain distance. And so we have them launch a cube, launch a ball which should go farther, and then this SPHUBE should be somewhere in between. We don't know. They're going to experimentally find that, then go back. Each one's different. An extension of this would also be to use a wind tunnel. The wind tunnel would show it in a different way, and that coefficient of drag should be correlated with what the simulation has. Again, looking at that back and forth, any error is what NASA scientists are doing. And they run the simulations, then they do an experiment, and they come back and see how they're doing, which is, I think, is a great way to model. And then the challenge part of this, to make it a competition, is to launch their own SPHUBE with the data that they've collected to reach a certain distance. And of course, they can go to different trajectories and look at the angle and run that in the simulation, which we thought was a great challenge. Beyond that, there's other challenges we can run, and using that data, rewarding them for different distances, things like that. Moving on to student resources and pages and assessment sources. Where there's reflection built in. We think that's a very valuable way for kids who are learning for the first time. What did you learn? How did you learn it? What did you think was exciting? What questions do you have still? Completion of the activities and grading those. Accuracy of the challenge of the SPHUBE launch at the end. Did you run your simulation accurately? Did you get it to where you want it to go?
So for the next steps, how we'll use the lesson back home, Well, I will definitely be incorporating launching rockets, one of the activities, and this activity would be a precursor to that, to give kids the idea of the trajectory and what's needed to launch a rocket. These are some things that will be used in speaking at the teacher meetings and at state conventions and sharing with other teachers.
Me personally, how we use these lessons, I do it all the time. I didn't realize it. When I teach, like I said, driver's ed, and we go into the process of parallel parking, we run a simulation on a computer, and they have to change the angle of the tire, and they have to see how that reacts, and if they go too fast, if they go too slow, and then we go out and practice it in real life, and then I show them in the car. I've got a whiteboard, and I show them how they've changed it and their angles and all these things. And I mention that. We're looking for a 45-degree angle here. Turn your wheels to this point. Run it on the simulation, then we out and practice it. How close were you? And so it's great to be able to have the vernacular now and to see how this is applicable to everyday life more than just the science part, which is a valuable, one of my most important goals. If they can do it in class, they should be able to do it at home. And if they bring the discussion that they have at home back to class, hey, my mom and dad had a great time talking about this, Mr. McKinnon. I get notes all the time from parents. That's extra credit. That's extra credit. It's a bonus internal reward for me, and they get physically extra credit. So I keep those notes throughout the year to remind me of the value of getting this to the science, to the kids, to having them take it home to real life. Most of the time, the parents don't know what we're doing in class either. So even though it's an introductory course, the parents are learning right along with the kids. A few other questions that we needed to answer. How can you ignite your school colleagues about ModSim? My math teacher and I, we both teach a language learning course in science. Hers is math, of course, the Shelton English kids. And she's going to love the math because it's hands-on. Let's go out, let's take a look at this. Let's go out and model it and compare those two things. The math, of course, is a simulation with numbers. I'm looking forward to sharing it and launching my SFUB and prizes, candy, and stuff at certain people and prizes during our different faculty meetings. And the earth science teachers that are around me, hate to say it, it's kind of a boring topic sometimes, and this is going to give them some wonderful things. My guess is that my earth science teachers have not even touched what earth science opportunities are available on the NASA Gov websites. So those are going to be really neat. Me personally, online, I'll be linking those and creating activities for that. Just me being excited about it, I hope we'll be able to enthuse others. Want to do?
Yeah, and where else do you plan on disseminating the ModSim information? Sixth grade classes often come into the junior high for a tour day, and that is one way to get the elementary schools fired up and show them some simple simulations. School board meetings, district meetings, and I had gotten a letter of intent from the University of Idaho, and I happen to be a 4-H leader, so they'll be having a state conference here in November, and 4-H is geared, they have 4-H clubs that have robotics, they have 4-H clubs that have rocketry, so this would be a great way to go back through the University of Idaho, and there's a lot of kids involved. I think we have 337 members in our little town of Emmett that are involved in 4-H in some way, so that would reach a lot of students.
It's exciting for us, and that enthusiasm is contagious. I've always found enthusiasm is contagious. We're enthused about it and excited. We want to say a huge thank you. I want to say my thanks to NASA because I always launched rockets as kids, thrown airplanes, made my little straw rockets, threw up the little Legos and watched them come down and made all these different things and changed things all the time. It was really neat to see that people do this and use their simulations and their models to get to space for real. So NASA is more real to me than just a name now, and I've really appreciated that.
And we'd also like to thank the members of the AESP, also the RTI, for providing all the lessons and all the opportunities we've had to listen to these engineers and to see really what they do. And unlike Aaron, I've never launched a rocket until I came here, and we did a group activity the other day where we actually had to build one, and we had a budget, and we had a purchase orders and checking, and it was really interesting and building the rocket. And I learned a lot of math. I learned a lot about computers, and I have to give a really big thanks to Mr. McKinnon here for being my moral support, because I don't have a great physics background, and he sure gave me an education. So thank you.
And we've designed our own high five for NASA, and so to say our goodbyes, we're going to give our high five.
NASA salute.
As we blast off and go into orbit.
Woohoo! Thanks, NASA.
Thank you, NASA. see me all pitting out.